A germanium crystal is composed of many germanium atoms. Each of these atoms consists of a nucleus with 32 electrons moving around it in 4 separate orbits. The 4 electrons moving in the outer orbit are known as the valency electrons. They are responsible for binding together the individual atoms of the crystal. The crystal lattice is static only at very low temperatures. But as the temperature increases, say to room temperature, thermal vibration is set up, causing some of these valency electrons to escape from their bonds. In this way, free electrons and holes are generated simultaneously. The reverse process, recombination, limits the conductivity of the crystal. The number of free electrons moving at random in an intrinsic germanium crystal is determined by the temperature. And the concentration of these free electrons, which is constant throughout the crystal, can be represented graphically by a horizontal line. At the same time, holes are also moving at random through the crystal. And their concentration can be represented by another horizontal line. In the case of intrinsic germanium, these two lines will coincide. If we now introduce into the intrinsic germanium foreign atoms having 5 valency electrons, arsenic, for example, each of these foreign atoms will give rise to an extra free electron. Consequently, the free electron concentration increases. And the horizontal line representing the electron concentration assumes a new level. With so many additional electrons present in the crystal, there is more chance of the holes recombining, so that the hole concentration decreases. Thus, the hole concentration curve will assume a lower level. This type of crystal is known as N-type germanium, because the free electrons are the majority charge carriers and the holes are the minority charge carriers. If we now return to intrinsic germanium and this time introduce into it foreign atoms having only 3 valency electrons, for example indium, an extra hole will occur for every foreign atom introduced. The resulting increase in hole concentration is shown by the new position of the corresponding concentration curve. In this case, there is an increased chance of electrons recombining, so that the free electron concentration decreases and the corresponding concentration curve will fall to a lower level. This type of crystal is known as P-type germanium, because the holes are the majorities and the free electrons the minorities. If we now take an N-type crystal and alloy an indium pellet to it, we find, after recrystallization, a region of P-type germanium situated between the pellet and the N-type germanium. Let us now study the behavior of this newly formed PN junction. In the vicinity of the junction, an electric field has been set up which acts as a barrier to the flow of majorities. Initially, during the formation of the PN junction, the barrier is very narrow, allowing majorities to diffuse and recombine from both sides. The result is a loss of majorities at both sides of the junction and thus an enlargement of the barrier. This enlargement causes a slowing down of the diffusion process until finally an equilibrium has been set up. Consequently, no current flows across the junction due to the two space charge layers which make up the barrier. The majority and minority carrier concentrations outside the barrier region are represented in the graph by horizontal lines. However, if we now apply a forward voltage to the crystal, the width of the barrier will decrease, and again a certain number of majority carriers will diffuse from both sides. The concentration curves of the majority carriers will remain horizontal, but those of the minority carriers will rise near the barrier. This rise in minority concentrations is directly related to the current flowing across the junction, which is equal to the current flowing in the external circuit. The equivalent circuit of a diode having a forward voltage applied to it consists of a junction in series with the resistance of the N-type material. In order to find the current voltage characteristic of the diode, we should first study the current voltage characteristic of the junction. Without this forward voltage being applied, the minority concentrations will return to the equilibrium level, which is here 10 to the 10th per cubic centimeter. In the junction characteristic, the situation is represented by this point, because both voltage and current are zero. When a forward voltage is again applied, the barrier width decreases, and the minority concentrations rise, for example, to 10 to the 11th per cubic centimeter. These deviations from the equilibrium level are proportional to the number of free electrons flowing from the N region to the P region, and to the number of holes flowing in the opposite direction. These numbers of charge carriers flowing across the junction determine, in turn, the value of the current in the external circuit. If the applied forward voltage is now doubled, the deviations from the equilibrium level, shown by the minority concentrations, will also appear to be doubled. But this is only because a logarithmic scale is used. The actual deviations, however, are about 10 times greater, and as these deviations are proportional to the number of free electrons and holes flowing across the barrier, the new value of the current flowing in the external circuit is also about 10 times greater. If the forward voltage applied is 3 times greater than its original value, then the deviation shown on the logarithmic scale will also be 3 times greater, whereas the actual number of free electrons and holes flowing across the barrier will be about 100 times greater. Thus, the number of charge carriers increases exponentially. Therefore, the current voltage characteristic of the junction must also have an exponential shape. Now that the junction characteristic is known, let us determine the characteristic of the series resistance. This characteristic is linear. The voltages across the junction and the series resistance must be added to obtain the voltage at the diode terminals. By drawing these two characteristics on the same graph, The forward characteristic of the diode can be determined. By constructing a circuit such as the one shown, the forward characteristic of the diode can be measured. A small change in voltage is seen to cause a large change in current. So far, we have only considered the forward characteristic of the diode, but the reverse characteristic is just as important. If we now reverse the battery connections, the junction will obviously be biased in the reverse direction. The barrier then becomes enlarged, with the result that no majorities flow across it. Thus, the majority concentration graphs remain unchanged. However, the two space charge layers that make up the barrier will, due to their polarity, allow minority carriers to cross. Consequently, the minority concentrations in the vicinity of the barrier will decrease. In this case, it is the minorities that cause a current to flow in the external circuit, and the value of this current is directly related to the decrease in the minority concentrations. With no voltage applied, the minority concentrations return to the equilibrium level of 10 to the 10th per cubic centimeter. Because both voltage and current are zero, the situation is represented by this point on the characteristic. When a reverse voltage is again applied, the barrier is enlarged and the minority concentrations decrease, for example, to 10 to the 8th per cubic centimeter. The numbers of charge carriers flowing across the barrier are proportional to these deviations, which are numerically equal to 10 to the 10th minus 10 to the 8th. The latter number is so small that it can be neglected. The same result is obtained when larger reverse voltages are applied. Clearly, the values of the equilibrium concentration set a limit to the numbers of charge carriers that are able to cross the barrier, and consequently, to the reverse current flowing in the external circuit. This limiting value of the external current is called the saturation current. Beyond a certain high value of reverse voltage, breakdown occurs, causing a sharp increase in current. In the equivalent circuit of a reverse bias diode, the series resistance can be neglected due to the high resistance presented by the junction. However, a leakage current flows over the edge of the junction, and this is represented by a resistance in parallel with the junction. The reverse characteristic of the junction is known, but we still have to determine the characteristic of the parallel resistance. As for any resistor, its characteristic is linear. By adding the currents flowing through the parallel combination of junction and resistance, the total current flowing through the diode can be found. The sum of these two characteristics gives the reverse characteristic of the diode. With a circuit such as the one shown, the reverse characteristic of the diode can be measured. A large change in voltage will give rise to a small change in current. If the positive and negative values of the current are plotted on the same scale, the reverse part of the characteristic will very nearly coincide with the horizontal axis. But by enlarging the scale for the negative values of the current, the reverse characteristic also becomes clear. Let us now consider a circuit containing a diode and a resistor, to which an alternating voltage is applied. During the positive half cycle, when the diode is forward biased, its internal resistance is so very small that the generator voltage is almost completely absorbed by the resistor. In the following half cycle, when the diode is reverse biased, its internal resistance is very large, and therefore the voltage across the resistor may be neglected. The behavior of a diode can also be seen if, in its equivalent circuit, the junction is replaced by a switch. When the diode is forward biased, the switch is closed, thus short-circuiting the parallel resistance. The behavior of the diode is then determined purely by its series resistance. Reverse biasing of the diode is equivalent to opening the switch. As the series resistance is small compared to the parallel resistance, it may be neglected. Thus, the behavior of the diode is determined by the parallel resistance only. For a supply circuit having a resistive load, the maximum permissible value of alternating voltage to be applied is determined by the breakdown point of the particular diode characteristic. Shunting the resistor by a large capacitor will cause the working point to shift, with the result that the applied voltage must be reduced to half its previous value. Higher voltages can be rectified by connecting 2 or more diodes in series, so that the voltage across each diode is kept within the permissible limits.